Yeah, it's fine. Welcome, everyone. I'm Donald Sharp. I work for Cumulus Networks, and I'm going to talk to you today about FRRouting. If I can make it go to the next slide. There we go. So what are we going to cover? We're going to cover how FRRouting came to be, and then some basic routing, and then advanced data center routing. And finally, we're going to talk a little bit about where I hope to take FRRouting in the future. So what is it? It's just another routing stack. It's the same thing that you can get from all the other major vendors. Today, development is supported by a large number of companies. Configuration is actually really similar to other vendors. There's two different ways you can configure it. You can actually configure it from both a file and an interactive CLI. FRR runs natively on Linux and many other platforms. The one caveat there is that all features actually only work on Linux. That's not true for all other Unixes. BSD and the BSD variants don't have all the features, and their networking stack is not near as advanced as what Linux is. FRRouting actually uses the kernel's routing stack for packet forwarding. We're control plane. We don't do any of that. And finally, we're GPL v2 plus. That effectively means that we have a couple other licenses that are compatible with with GPL we're being used as well. So where did FRRouting come from? It all started around in 1996 with a routing suite called Zebra, and in 2002. Quagga was forked from Zebra, and that continued on until 2016, where we forked from Quagga. And our first release was actually in January of 2017 with version 2.0, and now we're up to version 5, basically a year and a half later. So why'd we do it? We actually wanted a faster paced development. We wanted the ability to work with people in a cooperative way. We needed a CI system that wasn't available, and we also wanted the ability for people to work fast and make mistakes and correct them in a timely manner. We also really wanted community consensus on the features and how we did the work together. And this is all under the auspices of the Linux Foundation. All right, so this is the basic new work that we've done. The first 5 items, Babel, ERGP, NHRPD, PBR, and LDPD, are new daemons since we forked. I'll get into those a little later, what they are and how they work. We've added large communities, a bunch of EVPN support, RPKI, which is a public key infrastructure for route validation in BGP. You can do MPLS-based VPNs, VPN VRF route leaking. We've implemented 5549, RFC 5549. We've added hostname support, shutdown messages, and recently we just got FlowSpec. So that's actually, most of our work is actually in BGP, and that is the focus of what most people are interested in actually currently. In IS, we've added multi-topology support and SPF backoff. OSPF, we've got experimental segment routing, and it also supports 5549. We've added sparse mode to PIM, and we also added the ability to do VRFs, both using the VRF device and namespaces. The one caveat there is that not all daemons actually support VRF yet. You can really use VRFs with BGP, Zebra, PIM, and OSPF currently. And I don't actually have all the new routing features listed. You can go to the website at the bottom and see what we've added as well, if you're interested. So where do you get FRRouting? We actually do most of our work on GitHub. So you can go to github.com, FRRouting, FRR, download the source. We have we spent a lot of time recently working on our documentation. So we've got a pretty good dev guide on how to build and set up FRRouting if you want to build from source. We also have the ability for you to download RPM and RPM-based and Debian-based packages for a wide variety of platforms. Here's the packages that we actually provide, you can download right now. And the packages and, distributions and versions that you can download packaging for right now. So I list caveats for both BSD and Solaris-based systems. I kind of covered it already, but a lot of the new features that we've added do not work on the network stacks available on those platforms. So with new features comes new dependencies on kernel feature versions. So I just wanted to call out some of the major dependencies that we've introduced in the last year or so, year and a half. If you're using VRF, and that depends on the L3M dev device, which is the 4.4 kernel for limited and 4.8 for full functionality. Am I missing anything there, David? Is that right?
That's all right.
Yeah, it's good enough. Yeah. So
I always recommend 4.10 or higher.
Okay, that's fair. That's right. David's right. 4.10 or higher for all bug fixes that we're aware of currently. BGP EVPN support depends on the new NTF EXT learned netlink message, and also the ARP suppression feature available in 4.17 for the NTF EXT learned and 4.14 for ARP suppression. To get PIM-SM going, we needed to actually add some RT and multicast, RT and multicast netlink messages upgrades so we can get a bit more data from the kernel. And also, we also needed to add a new callback via the PIM socket, which is IPMGP message wrong VRF hole, to allow for register packets to work. All right, so once you've gotten FRRouting compiled and ready to go, well, how do you start it? It's pretty simple. We've integrated with system control now. You can just do the normal system control start, stop, reload. Did I miss anything? Start, stop, yep, restart, reload. It does what you actually think it should do. The one thing that's actually interesting that we've implemented is the reload feature. If you modify the FRR.conf file, which is the configuration file for FRR, and then issue a system control reload, it will take the configuration file, compare it to what you actually have running versus that file, and apply the diffs so you can get consistent. And here is an example on the side here, the system control start FRR, and the V2I shell is the interactive shell that people can use. Typically, one of the first things that people ask me after they've got it up and running is, what the heck's going on? Where did my login go? That's been one of the harder points to get across. If you're not sure where your login is going, type show login inside of V2I shell, and it will tell you where each daemon thinks it's sending its output to. It's actually kind of important because people can't find it sometimes. Then we actually support 3 different types of destinations. You can send the output straight to syslog, you can log it to a file, or you can log it to standard out. Standard out really is only useful for a developer and you're doing some debugging. It's not for production usage. The other common question that people ask is, why does my log file have no output? We've actually designed FRRouting to not be chatty, unless debugs are turned on. This is mainly because there are a lot of platforms that FRRouting is run on that don't have good hard drives or S-disk or whatever they are. SD, yeah, sorry. And if you're not sure what to figure out what's going wrong, under V2I shell, type debug, protocol name, and question mark, and it'll tell you the different types of debugging you can turn on, which will go to your where you've set your log file, your login to go to. That's one of the first things that I do. I don't always remember all the debugging commands. I just know that I can hit question mark, which will give me help. And that's actually true as an aside. If you want help on any command, question mark and tab are your friends. So how does FRR work? We have a daemon called Zebra, which provides the RIB functionality and control of what gets inserted into the kernel. So a routing protocol like BGP or OSPF, they all connect to Zebra. And they do things like tell Zebra to install routes. And Zebra takes that and talks to the Linux kernel via the netlink bus to install those routes. The one interesting thing about Zebra is that we actually have 2 netlink sockets. One's for just listening for new netlink data from the kernel, and one's for actually sending commands down. All right, so in the previous, how do I go backwards? Sorry. Let me go back a slide. My presentation view is not great. So in the previous slide, actually, if we looked at it real quick, there was the ZAPI protocol referenced. That's the protocol that Zebra and all the routing daemons use to talk to each other. So why didn't we just use netlink? That's a question that I get sometimes too as well. When ZAPI was actually first written, we didn't have the netlink protocol in the Linux kernel. So we had to have something. Additionally, netlink doesn't provide the same data communication needs that a routing daemon needs. Things like redistribution, passing around router IDs, turning off BFD, next hops, and passing around capabilities. If you're interested in looking at more, you can go into libzclient.ch. That's where we've defined the ZAPI protocol and how it works. It's essentially just a stream of data being sent from the routing daemons to each other, and it uses named sockets. And right now, it's only really used to talk from FRR daemon to FRR daemon, and we actually do change the format quite often. So it's just something to be aware of. All right, here's just a quick slide to give you places that you can learn more about FR routing. All right, so I'm going to talk about basic routing next. Why? Actually, I'm just going to skip this slide. So why routing? Networks today are becoming increasingly complex, and just adding a static route isn't going to cut it for connecting computers together. And additionally, networks are not getting simpler. With things like VMs and containers, you're actually starting to need to have the ability to route between VMs on the same host. FRRouting allows you to do that. So routing allows us to control all this chaos that can happen in a network. And so one of the really great things about this is that Linux now has the ability to interact with the entirety of the network via standards-based approach. So if you are using a Cisco or a Huawei or a Arista for routing, you can put FRRouting on your host or on your server and connect to those machines and get routing from them. One of the other subtle differences between the Linux kernel and the Zebra is this idea of a RIB versus FIB. So a RIB is a routed information base. It's commonly called a control plane. This is what FRRouting does. That's what Zebra actually does. Zebra is in charge of the RIB. It makes decisions about what gets installed and how it's installed. And the FIB, or the forwarded information base, is the data plane. This is the Linux kernel. And in general, when you talk about routing, there's this clear line between the rib and fib and who owns what. At the bottom here is just a simple look at how the kernel and FRR both show the same information. So I'm sure you're all familiar with when you do a IP route show on the Linux kernel, one of the items that it gives you is a metric. And the Linux kernel uses that metric to decide which route to forward, to decide how to route packets based upon the metric, the best metric. Well, the problem with metric is that every single routing protocol has a different idea of what a metric is. So, like for instance, RIP here uses hop counts and is only allowed values between 1 and 16. EIGRP uses a composite metric, which is a uint 32T. And OSPF is a link state distance, which has a range of starting at 100 going up. So how does Zebra decide what's the best metric to use? So routing protocols or routing suites have this idea of administrative distance. We've decided a priori that each routing protocol has a different distance. So if RIP and BGP both install the same route into Zebra, Zebra is going to look at those routes and decide that the BGP route is better based on this administrative distance value we've assigned to it. Lowers wins, and it's a number between 0 and 255. On the right-hand side is the basic values that FRRouting uses for administrative distance. This is actually also consistent with pretty much every other vendor out there. There is no standard here, it's just everyone's kind of agreed this is what to use. All right, so how do I determine what to install? This is just an example slide. I wanted to show a kernel route, the K there on the left-hand side. The 4321/32 route is a kernel route, and the parenthesis 255 8192 is the admin distance and metric. And Zebra, if I enter a IP route 432132 going out interface ENP0S10, that creates a static route in Zebra. So Zebra at that point in time makes a decision that the static route has a better admin distance, and it selects it. And you can tell that by the greater than symbol. That says that Zebra's decided that that's the one we want to use. And on the right-hand side is the kernel, showing what the output of IP route show is. All right, so with the Linux kernel, anyone can put routes into the kernel. And as a routing suite, we have to be able to interpret those routes and figure out what admin distance they have so that if a routing protocol like BGP or OSPF or RIP install the same route, we have to know who wins. So what we've done is that the kernel metric for routes that are not generated by FRRouting, we interpret the kernel metric as two pieces of information. The high order byte becomes the admin distance, and the low order byte becomes the metric. And so if you look at the example here, is we do an IP route add, 432132 dev ENP0S9 metric 4 billion something. And further right, we have the hex number that translates to, which is 0xFF002000. So FF becomes 255, and the metric becomes 2000, or 8,192 decimal. So why is this important? So if you're actually going to be using VRFs inside of FRRouting, you need the ability to terminate. Actually, I should take a step back. So of the Linux kernel has this concept of table lookup and rule lookup. So when you tell the Linux kernel to do a lookup, when a packet comes in and it has to do a lookup and it goes, I need to look up in table 1000, and from the IP rule show, we know what table to look at. And if I'm using VRFs, if I'm using VRFs, I do not want that route search to leave that table, because the Linux kernel will, if you don't have a default unreachable route, will go to the next table. In this case, so it would go to 32,765, and then use rule 32,765, then rule 32,766 if it doesn't find a match, and finally we look in 32,767. So what we've done is that the metric that we've installed the default unreachable route in the kernel can be interpreted as a high and min distance. And because of that, we also want the ability for FRRouting to override that default route if some other routing protocol wanted to put something in. All right, so I just kind of talked about VRFs, and FRRouting supports two different types of VRFs. There's the VRF device. I'm sorry, I've skipped a slide here. So there's VRFs are separate tables for collection of different interfaces. It provides layer 3 segmentation, and it also provides the ability for routing protocols to install the same routes into different tables. Now, why would you want to do this? There's a whole bunch of different reasons, but the main reason is that you want to have a separation for some reason or other. Say you have a telephone network and you have a data network, you want them to use different routing tables. I'm a provider, and I have a whole bunch of customers that are connected to me, and I don't want their routing, and those customers don't want their routing tables to be mixed, and they don't want any of their packets to end up in the wrong place. So that's what a VRF provides you. Security segmentation. I have a requirement from some security organization saying that these packets must stay on this network. They cannot go anywhere else. And the other reason for VRFs is I have an overlap in IP range from when two companies start to merge. And down at the bottom, I have a link to David Ahern's VRF tutorial for how it's actually implemented in the Linux kernel. So FRRouting actually has, yeah, sorry.
Just a question. What's the difference between, like practical difference between VRF and network namespaces?
I'm going to cover that here.
Okay.
So the practical difference is that a VRF device creates a master device that you attach all the interfaces that you want to be in that VRF to. Route lookup is done by a new rule inserted into the kernel, and that causes the VRF device to cause the fib lookup to go to the correct table. This also allows route leaking via just installing a route with an appropriate outgoing next hop. So lookups are extremely easy from a RIB perspective. And the other so the Linux kernel, you specify next hops by a gateway and device tuple, right? And you can also do just gateway by itself and or device by itself. But if I want to do route leaking across VRFs with the VRF device, I have to specify an outgoing interface, otherwise it will not work, right? All right. So what is a namespace by you? So the way namespaces work is that you create the namespace, and then you move your interfaces into that namespace. Route lookup is fairly similar. You look up in the default table for each namespace. The real big caveat here is that route leaking can only be done by creating a bridge outside the namespace and installing taps into the different namespaces. Or I need to go to the front panel and where I've put those interfaces in different ones and plug the cable in between the two of them. So that's how I can do leak in between VRFs and a namespace space. That is totally heavyweight. If I want to do more than a couple VRFs, I all of a sudden have to manage a large number of bridges, a large number of interfaces, and I don't get easy route leaking by a simple route table lookup that the VRF device provides you. So again, namespaces are like a VRF, but not. They're really heavyweight, and I wouldn't recommend using them. Yeah. Anything else? Yes, sir.
Hi. Is it possible to create the VRF interface directly from the FRR, because I'm playing with it and I need to do it on systemd and then start there and then...
So that ability is not there right now. Okay. And when we implemented the VRF device, the VRF functionality in FRRouting, we were under a heavy time pressure, so it just wasn't done. The Cumulus, where I work, also has this idea that you kind of render under Caesar what that belongs to Caesar, and VRFs are an interface, and interface control and creation is controlled by IP Route 2. Okay. That's kind of the decision we made. David, you want to? I did that on purpose.
Okay. Other question is not related to VRF, but feature demand for BFD. Is there a future for it?
There's a pull request for it right now.
Okay.
There's actually two different ways. So currently you can get BFD integration if you go to the Cumulus GitHub page and download the PTM package.
Yeah.
And that kind of sucks for a lot of reasons, right? So
I tried it.
Yeah, it sucks. The integration is harder. There's the gentleman named Rafael Zalima who's taken that PTM BFD code and has started integrated into FRRouting. And there's a pull request right now that we're working on trying to get in. So hopefully the next month or so we'll have BFD support directly inside of FRRouting.
Okay. Thank
you. Just to add some additional words to, so the request to add the ability for FRR to create VRFs, the decision at the time, as I recall, was you don't use FRR to create things like bridges, which are connecting devices for layer 2. So the decision was like, well, let's not do the same thing for VRF. So that way you have an interface manager whose job is to create the different networking features like bonds, MAC VLANs, bridges, VRFs, and its job is to connect them all together. So it is something that could be done because it's a routing concept, but at the same time, the argument is that you're connecting a series of devices together, which becomes more of an interface manager domain. So that was part of the argument as well.
Yeah, exactly. Render under Caesar.
Yeah.
That which belongs to
And
Caesar.
then about the network namespaces, when you look at what a network namespace is, it's not just routing tables. So the idea of VRF is just to have multiple routing tables, which is essentially a policy-based routing to say these lookups go to this table, these lookups go to that table. Namespaces are a complete network stack separation. So everything from your devices all the way up to your sockets. And so that's why, because it is separate tables, you can use it for VRFs, and certainly many companies do. But every single company that's done it has learned that it's an extremely heavyweight, extremely painful solution for what you need for layer 3, which was the motivation for doing the VRF device.
Yeah, managing a bridge interface for every single time you want to do a route leak is a huge task, and keeping that right. So the one thing I would like to go back to, can we create VRFs inside of FRRouting? We just need someone to program it up. So someone just needs to take the time and do it. And and we'd take it. So if anyone wants to do it, feel free, from my perspective.
I think there is a good feature between namespace and VRF. I can create a tunnel using default routing table and put the tunnel interface inside the VRF without anything any complex modification.
Yeah.
Sure, that would work. You're right. All right, so in this next section, I'm going to cover basic topology and some basic configuration of some routing daemons. I'm going to use this topology for what I'm talking about for the next little bit. There's 5 routers all connected. You can see the IP addresses for everything. If you see an IP address that ends in .1, that comes from R1, .2 comes from R2, .3 comes from R3, and so on. And the loopback interfaces are in the 192, 168, 240 range. And here's the configuration files I'm using for everything. All right, so what is BGP? BGP is what is used to make routing decisions on the internet. If I'm connecting a company to another company, or I'm connecting to a service provider, you're going to use BGP. It connects autonomous systems together. It has a policy language that is both rich and featureful to allow operators a very fine level of control. In general, there's 2 levels of modes of operation for BGP, iBGP and eBGP. I is internal, E is external. If you're doing internal BGP, it's usually one of 2 things. It's route reflectors or full mesh. I'm not going to spend a lot of time talking about iBGP. I'm going to really spend more time talking about eBGP. BGP is considered a path vector protocol. It uses an AS path to determine what routes to install. And we use the AS path also for loop avoidance. So if I get back an AS path route, a route with an AS path that has my own AS number in it, I know it's a loop, and I know not to install it. I'm also going to greatly simplify BGP route selection. It's a complicated process. There's a whole RFC for it. But the basic idea is what I'm going to cover. BGP is layer 3 only. It uses TCP/IP for connections. And the bottom 2 bullet points are, the first one is a book by Dinesh Dutt, which is BGP in the data center. But it's a really good book that if you want to learn about BGP, it's a great thing to read. And if you really want to be kind of masochistic, you can read the RFC. But who wants to do that? All right, so how does BGP determine a routing path? So in this slide, I want to show how R1 would decide to reach R2 from a BGP perspective. So a side note here, AS5 is the autonomous system for R1, R2 is AS10, R3 is 15, and so on. And you build the path using the autonomous system. So if I'm on R1 and I want to know my route to R2, I need to compare all the different paths I have in the network. So the first one is directly from R1 to R2, and that's the AS path of 10. And the second one is the middle, which is from AS20 to 15 to 10. And that's a length of 3. And the last one is, on the bottom, is 25, 20, 15, 10. So as I mentioned earlier, the AS path chosen is the shortest one. And in this case, the shortest one is the direct connection between R1 and R2, and that's the route it would choose to get to R2. The route it would choose to install to get to R2. So this next slide, I wanted to show an example of ECMP. So if I wanted to get to R3 from R1, there's 2 paths that would actually equal. So the top path, which is 10 to 15, and the middle path, 20 to 15, and that would be considered ECMP, and we would install both next stops going from R2 and R4 from BGP's perspective. And then finally, the third one is the 25-2015. I'm going to skip this slide. This is the same thing showing how it works for R4 and the same thing for R5. I think it's kind of self-evident. You can come back and look at it later. So BGP, to set up, you need to know two basic things. Who am I peering with, and how am I deciding what routes to include? So that's, in a nutshell, that's how you configure BGP. You specify your neighbor. So in this case, we have neighbor statements, neighbor 192.168.210.2, 4, and 5. And I have to specify my remote AS number as well. BGP by default, if I set up neighbor relationships, will not move routes around or pass them from neighbor to neighbor. You have to tell BGP what routes to include. A common way to do this is you'd say redistribute connected. Yeah, and the network, so yeah, so you, in BGP, you either must use a redistribute statement or a network statement. Network statements only import existing prefixes that are in the RIB. And if you want to turn that off, you can just do no BGP network import check, and any network you've entered would automatically be included. Again, I'm not covering policy. Policy is covered by route maps and AS lists and a whole bunch of other stuff, but it's too complicated to really get into in a reasonable amount of time. I want to call out the multipath relax. That allows BGP to use different AS paths, but the same length as ECMP. And finally, each router needs to have, sorry. And each router needs to have the neighbor IP address set for it to work properly. So I kind of didn't show all the different setups for R1 to R2 to R3 to R4 to R5, but it's basically effectively the same. You have to create a neighbor statement, and you have to specify if it's the autonomous system of the neighbor. So after you've done that, you do a show IP route, and you can see that we have a whole bunch of BGP routes. All right, so I've set up BGP and it's gone to hell. How do I fix it? I use most often show BGP IPv4 unicast summary and show BGP IPv4 unicast. The first one shows me the neighbors that I have configured and the number of prefixes I have received from that peer. And the second one shows me all the different paths. And the two most common debugs I use is debug BGP neighbor events and debug BGP updates. My most common mistake that I make when I set up a BGP peering relationship is when I set up BGP is I forget to set the neighbor address correctly. I mess that up all the time. It's really easy to mess up. You're looking at me strange, David. No. This is just some quick debugging examples. And what the tables, what the output actually looks like. All right, so I'm going to talk about OSPF next. OSPF is considered an interior gateway protocol. It uses link state routing, and what that basically means is that each router floods information, all known information about itself, and every single bit of information is received from every single other router to everyone else. So it is pretty heavyweight in the fact that there's a lot of data being sent. If you just have a couple of neighbors, it's not that big of a deal, but if you have a lot, you're starting to send a lot of data around. It uses, I always mess this name, Dijkstra's algorithm to figure out what to install into the RIB. It also uses IP or layer 3 to advertise routing information from OSPF router to OSPF router. There's two different OSPFs. There's OSPF v2 and OSPF v3. I don't know why they did it this way, but v2 is IPv4, v3 is IPv6, and v3 also provides the ability to do IPv4 and IPv6, but no one does that. I don't know why. For policy control, OSPF uses areas, and I'll get into that in a second, but areas allow policy. It's kind of beyond the scope of this talk. And if you do have more than one area, you must also have an area 0. All right, I want to talk about how Dijkstra determines the best route to use. Dijkstra actually has some optimizations that are great for computers to make it faster to determine. I'm going to kind of skip over that a little bit because it ends up being the same. So the numbers between between R1 and R2, there's a number 60. That's the weight of the interface that we're going to be using for Dijkstra. And so R2 and R3 is 60, and so on. So from R1's perspective, if I want to get to R2, the best weight of all the three different paths is 60. So that's what it's going to choose. So the second path is 100 plus 5 plus 60. That's 165. And the third path on the bottom is 60 plus 60 plus 5 plus 60. So the next thing I wanted to call out, so from R1 to R3, if you recall for BGP, BGP had an ECMP path between R1 and R3. That's not true with OSPF with the examples here. So R1 along the top, the weights are 60 plus 60, and that's 120. But in the middle, 100 plus 5 to get to R3 is 105, so that's a better weight, and that's what the route that will be used from OSPF's perspective. So I'm just trying to call out here a key difference between BGP and OSPF and how they determine routes. This is just further examples of the same thing. I'm going to skip it in the interest of time. All right, so on the left here is all you need to do to configure OSPF. Router OSPF, network 000, area 000. And you put that on every router, and you will have a working OSPF network. It's not great for more than a handful of routers, but if you're doing something simple, that's what you would use. All right, so I've configured OSPF, and how do I debug it? I use show IP OSPF, interface, neighbor, and database database router as commands to figure out what's gone wrong. And my two most common debug statements are debug OSPF packet and debug OSPF NSM. And it's just a quick debugging examples. All right. The next routing protocol I want to talk about is ISIS. It's also considered an interior gateway protocol. Like OSPF, it uses a link state, and it floods all router information about every router it knows to every other router. Also uses Dijkstra. One of the main differences between ISIS and OSPF is it uses layer 2 for connection between two routers. And the protocol it uses is CLNP. I don't know a whole lot about it, but it's layer 2. ISIS is considered really easy to extend due to its TLV support and its packets. You can basically carry in arbitrary payloads. For policy, you can have 3 different areas, level 1, 2, and 1.2. 1 is just an individual area of a bunch of routers working together. I use 2 to connect areas together, and level 1.2 is for connecting multiple areas together. So this is a basic example of ISIS setup. If you'll notice that, and under OSPF, you just had to have a network statement. You can't do that in ISIS. You have to go to every single interface you want to be included in ISIS and say, use ISIS. And then finally, you need to configure a router is statement with a word, an arbitrary word, like I chose EVA here. And that net 47.0 whatever is a holdover from early is where each, and it's a holdover, and it originally, you could use it to send information about how that particular router was being used in the network. And I think people kind of found it didn't really work too well. But you still need to have a net statement, and it's got to be a 6 to 20 tuple of data, and they have to be unique. I don't know why. And you basically need more config than OSPF because is does both v4 and v6. Here's an example of the is this configured and working. And here's how I've debugged is in the past. Show commands, some basic show commands, and the basic debug commands. Here's some sample output. All right, so I've gone over BGP, OSPF, and is. Which one should you use? The reality is that you use what's best or what you know best. They're all complicated. They all have their own pluses and minuses. And if you're just setting something up for yourself or for a small network, use what you know best. BGP scales better than either OSPF or is, mainly due to the lack of link state flooding. And finally, BGP can also handle many AFI-SAFI combinations that are missing in other routing protocols. And it's very commonly used for both an overlay and underlay networks or VPN networks. All right, so I haven't talked about a whole bunch of different protocols, and I just wanted to mention them at least real quick. So if you want to do non-link local multicast routing, you're going to use PIM. If you're going to do, and I've lumped RIP and EIGRP together because they're both distance vector routing protocols. Most people don't use RIP. It's ancient, not really great. And the EIGRP and FRRouting is not ready for production use right now. It works, but you can easily make it fall over. NHRP is really, really complicated, and has a special use case that's not really that common. Basically, I want to have a one-to-many connection. That's what NHRP is used for. It's the DMVPN solution. PBR is policy-based routing. Again, it's limited use cases. It's static routing with a twist. You can do things like match on source and dest and ports to figure out how to route that packet. FRRouting has Babel, which is a wireless mesh and home routing. And finally, we also have LDP, which is label distribution for MPLS. So what does FRRouting provide? It provides you the ability to run routing anywhere in your network. So traditionally, you go to your network vendor and they sell you a box that you go take to your network and you put it down and you plug your cables into it and you plug your hosts into it, and the two don't mix. And I think we're discovering today with the proliferation of hosts and VMs on hosts and containers and advanced routing use cases, it allows you to run your network and stack directly on your Linux box wherever you want, and to provide the networking that you need wherever you want. One of the problems that networking vendors have is that they only have control of the box that they sell you. FRRouting allows you to have control of your network everywhere. The other great thing that it provides is it allows you to connect to those closed source vendors, just using the standard routing protocols that they are using as well. All right, so the next section is advanced data center routing. I'm going to cover modern data center architecture, what it looks like, RFC 5549, and a very quick overview of BGP VPN. So the modern data center is a Closs network. It's named after Charles Closs. Some guy, I think he worked at Bell Labs, invented this back in the 50s or 60s. So it's been around for a long time. So a Closs is typically a layer of routers or switches on the top called the spine with leafs or tors underneath it that are connected. And you can see each leaf is connected to each spine. So what does that provide? It provides known latency between each host in the data center. It provides guaranteed bandwidth for your applications. It's really easy to build because they're just plugging in and doing the same thing for every single leaf tor and every single spine. And when something does go wrong, you've limited your failure scope. So typically, what we have on the left is called a pod, and that's a data center. That's basically just a unit of work or control. And if I want to have more pods, I just add another layer and add another layer, add more spines, and call the middle layer leaves. So what is the other thing that the data center, modern data center architecture gives you is ECMP. I can do multipath between all my different hosts without using any layer 2. And that gets rid of SDP, which is extremely, SDP will shut down links between different redundant links, and that limits your bandwidth. And finally, MLAG that is used in the data center is extremely hard to get right. So what is RFC 5549? It's the ability to have V4 routes with V6 next hops. So think about it from I have a V4 pod and I want to get somewhere else, and I can specify how to get there with V6 next hops. So why would I want to do that? Well, I don't have a lot. Maybe I'm running out of V4 address space, and I don't have a very limited how much I can use. Well, this allows you to get around that. It's really ideal for data center point-to-point links. This allows you not to have to put a V4 address on every single interface in your data center. And it's also commonly referred to as unnumbered. So in this example here, if I put an IPv4 address on every single interface on between the spine and the tors, I need to have 45 IPv4 addresses. Excuse me. And if I convert to using 5549, I can reduce the address space to 9 IP addresses. In this particular example, I just need 1 IP address for the loopback on each of the spines and one for each of the tors. Now, obviously, if you have a bigger data center, the ratios changed based on how you've built out your class. All right, so unfortunately, the Linux kernel does not really allow you to do V6 next hops currently. It's something that's coming, right, Rupa? Soon. So how does it work? We have to actually cheat. We have to derive the MAC address of the peer via V6 router advertisement. And so what we do is we create router advertisements, and from the peer, it'll give us its link local address, and from that we can derive the MAC address, and using that we can insert into the neighbor table a IP address of 169.254.0.1, the interface and the MAC address, and I can use that as a next hop. And at the bottom of the slide here, I wanted to talk a little bit about how this actually works from FRR's perspective. So I have to tell it to use unnumbered. And what that causes BGP to do is send a message to Zebra saying, hey, could you turn on router advertisement for that interface? Zebra says, sure, I can do that, and it sends a router advertisement. So I kind of have the arrows going to the right from Zebra to the kernel. I kind of really mean Zebra to the network, but from Zebra's or FRRouting's perspective, it's sent out of socket and it's taken care of by the kernel. That's why I've kind of left it there. I don't want to give the impression that it's actually really talking to the kernel. So I sent out a router advertisement. Eventually, I'm going to get a router advertisement back from a neighbor out that interface. And at that time, Zebra does two things. It installs that neighbor entry that we just talked about, the 169.254.0.1, and the MAC address. And it also tells BGP the link local address for that interface. BGP takes that data and forms a TCP connection using the link local address of the peer. And at that point in time, it goes through the normal BGP mechanism of gathering, bringing the neighbor up, and then gathering routes from it, and then it installs the route. And Zebra will see the V6 next hop that BGP installs and go, oh, I should use the 169.254.0.1 next hop instead. Sujit, you're looking at me funny. Okay. All right, so how do I set that up in BGP? It's actually pretty easy. At the top, I have the interfaces, and if you note, they don't have IP addresses. So we removed those. And the second thing is the neighbor statements have changed subtly, and I have neighbor interface, the interface, actual interface name, and then the keyword interface, and then the remote AS external. That's I'll come back to the external in a second here, but the neighbor statement becomes the interface you want to use. The remote AS, we've added a feature to FRRouting called remote AS internal external, and what that basically means is that if I write internal, I expect the autonomous system from my neighbor to be the same as myself. And if it's not, I'll reject it. And the second one is external. If I receive a different AS than mine, I will accept it and reject the same. So why is this good? Well, from a configuration perspective in a data center, it reduces my config to something I cut and paste. I can take that config and put it on every single router in my network, fixing the router BGP correct AS number if I've changed it. But it becomes incredibly simple. Since it simplifies my network, I've reduced my errors, and I've got this cut and paste configuration across a large section of my data center. So I wanted to call out the subtle difference from over here on the left, the FRRouting perspective of the route and the kernel perspective of the route. So we have the BGP route for 240.2, and you can see it's got a V6 address. And on the right, we've installed it different with the 169.254.0.1 and the dev SFAP1. And if you look at the bottom here, we have the neighbor table entry for each of the different neighbors I've specified. And the red one is the SWP11. All right, so we also have the ability to do OSPF Unnumbered. I actually kind of hate the name. It's awful. It's not unnumbered, it's the same IP address everywhere. So BGP, I didn't have to put an IP address on the interface. OSPF Unnumbered, I have to put a /32 on an interface. I can put whatever /32 number I want to put on, just as long as it's the same one. On the left is the configuration. So if you recall earlier, it was router OSPF, network 000, area 0, and that was it. Well, to do unnumbered OSPF, I have to change to configure each interface as a point-to-point and specify if it's in what area it's in. And over here in the middle here, we can see that each interface has the same IP address. And at the bottom is a quick documentation on how to use it if you're interested for yourself for further. And this is just the results of Unnumbered. All right, so why do I actually need L2 in a data center? There's still a lot of legacy apps out there that still need layer 2 connectivity. I'm doing link local multicast, typically for service discovery. Maybe I only have the MAC address of whom I need to talk to, or they're not using TCP/IP. In a data center, typically hosts under a TOR can only talk to each other, but maybe I want to have hosts under a particular TOR talk to another set of hosts under a different TOR. So that's why I need the ability to pass layer 2 across those. And finally, there's an assumption that IP addresses stay the same even when a host or an endpoint is destroyed and recreated elsewhere in the network. This is especially true for VMs or containers. So how do we solve that? We typically solve that with VXLAN encapsulation. It provides layer 2 segmentation over a layer 3 network. The L2 over L3 network allows you to leverage all the data center links, and you have ECMP paths to get to the host you're interested in. VXLAN encapsulation is just a bunch of tunnels, effectively, right, Rupa? It's a lot more complex control plane, but allows a lot better higher availability. All right, so in this example, I'm going to rework the topology a little bit. But the thing I want to call out here is that R1 and R3 become the leafs or TORs in this VXLAN network. R2 becomes the spine, and R4 and R5 are going to be configured with the same /24 network. Here's my interface configuration. R4, see, has 192.168.244, and R5 has the 214 is what I'm really interested in here. 192.168.214.4 and the 192.168.214.5. So how do I create it? You create a VXLAN interface, and you create a bridge that connects the VXLAN on R1 and R3. All right, so what is BGP EVPN? It takes VXLAN networks and extends the control plane across the data center. So it's layer 2 networks across layer 3 underlay networks. It's a unified control plane. And so the way it really works is it distributes the MAC addresses around the data center. So in the picture here, the MAC addresses for A, B, C, D, E, and F would be distributed to all the leafs here. And if, for instance, if E wanted to get it to A, all I would have to do is just send a packet, and the MAC address would allow you to get there. There's a EVPN in the data center book that you can get for free. If you go to the Cumulus Networks, that you can sign up for it, and it says, you give your email and they'll give you a book for free. But it's a really good book, and it really explains how EVPN works in the data center. Rupa also has from a previous NetDev conference, her EVPN or Linux Bridge tutorial that I've linked here as well. So EVPN setup is actually pretty simple for a basic use case. The only thing you really need to do is add this new idea of an address family, and it's the address family L2 VPN with the EVPN SAFI. On R1 and R3, all you really need to do to get it to work is specify advertise all VNI. So you notice R1 and R3 have it, and R2 just is the spine and doesn't need to have that. BGP also has this concept of not using an address family unless you tell it. So you do need to specify that you want to use a particular neighbor in a particular address family, or that will not work. So this is I've configured BGP into some show commands. And the big one here is the show BGP L2 VPN EVPN. Their EVPN has 5 different basic route types. In this example, we're only using route types 2 and 3. Route type 2 is the MAC distribution via VXLAN across the network, and type 3 specifies how to handle the broadcast, unidentified, and multicast traffic across that network. All right, so where are we going with FR routing? Currently, the main big thing we're working on is a Zebra rewrite. I think it was mentioned in an earlier talk today that David Ahern's working on rewriting next hop groups, breaking out routes and next hop groups in the Linux kernel. Well, that's going to bring a new netlink protocol messages that we need to actually use. So that's something we're working on. We're actually doing another CLI rewrite again to take advantage of netconf and Yang. There's a pull request, semi-active pull request that started that will start that conversion. That's going to happen in the next couple of weeks, hopefully. And the other thing we're actually thinking about doing, and some people have actually started doing, is full remote data planes. And what I basically mean by that is that the Linux kernel would no longer be the fib. It would be a entirely different something else. So you can basically, it'll allow you to install routes onto another device anywhere, as long as you set up the appropriate communication methods between the different devices. And people are asking for a whole bunch of features, and we kind of need people to work on them. So if you're interested, we have a whole bunch of feature requests. And finally, the last thing is we're going to have type 4 EVPN, which is multi-homing. All right, that's it. Thanks. Yes, sorry, questions. Where do you want me to go?
Previous, the slide before.
Oh, sure.
So this, 3 questions. 4 points, 3 questions. Netconf Yang,
Yep.
is that going to be built into FRR? Is it a separate daemon? Is it?
It's going to be built so effectively, when we did the CLI rewrite a year and a half ago or 2 years ago now, we had to go through and touch every single frickin' daemon and rewrite everything. It's going to be the same thing. It's probably except more invasive and intrusive. So the goal from my perspective is to provide a middle API.
But then you don't touch it.
Well, you do because we want to take the CLI and pull it out and use that middle API.
So this will be the last time you will touch it.
I don't believe that one.
But the design would be done.
So the goal is to provide an API for configuration between each daemon, and so FRR was written with a very tight coupling between CLI and implement it, and we have to rip that apart, put that middle layer in, and then once we've done that, you can have the netconf and Yang talking through, and then the reality is anyone who wants to write their configuration du jour, they can just write to that API and things will just work. You said you had 2 more questions, Sujit?
Yeah, no, I'm still trying to, legacy, that's all. I'm not confident I'm going to use that. Great. Full remote data planes, what's the backend for that? Is it Netlink as well? Or?
So it's the FPM, Forward Plane Manager. So it's going to change. And I think we discussed this as well, but to give everyone context, I want to have, we're going to rip out, so currently Zebra talks to the Linux kernel via synchronous methodology. And so basically what that basically means is that we install a route and then we wait for an answer. So we need to rip that out and make it so that you say install this route, and at some point in time in the future we get the notification back saying it was successful or not. And so for every single type of thing you want to do to the kernel, we have to do that, change it from synchronous to asynchronous, clearly define that API, and then program everything to it. So one of the real problems we have is that the different kernel interfaces are tightly coupled with Zebra. So it's just, again, ripping things apart, putting a middle layer in, and then programming to it. Does that answer your question?
It answered my question from the daemon's perspective. So that's what each of the daemons.
And so, okay, I'm sorry. So to further,
I was waiting for you to get to
I know, you're right. It's tough being a presenter, but you know that. So we rip it apart, put that middle layer in, and I want to be able to write a whole bunch of modules that I can pick and choose. I want to use the Linux kernel module. Plop. I want to use a forward and plane manager that someone wrote. Ploop. And they just have to write to that API and respond to it and pass up it worked or not.
Right, so you have to fix that, no question. I'm saying on the back end, something you might want to think about is making the wire protocol the new sort of Zebra back end, if you wish.
There's ongoing talks about how that is properly done right now, and there's some contention.
Netlink might be an interesting answer, because one of the things that Netlink itself.
So you know FPM uses Netlink, right? Did you know that?
No, I didn't know.
It does.
Talk to the hardware.
There's two different ways you can use the FPM. There's the Netlink and there's these other protobuf bullshit. Whoops, sorry. That
I have to start getting offended on that. Okay, got it. So that's great. But sorry, Netlink has this great thing that you can do steering and filtering and load balancing. So that's easy. Sorry.
Yeah. The only thing to keep in mind with Netlink is that you will need a proxy function to ensure that the byte order is
Correct.
Yes, that's the only thing.
But he already has that. That's a Zebra back. He can do that before. Sorry.
I was just curious, who uses the...
I'm sorry, Rupa, I can't hear you.
Oh, really?
You speak so
Why does
soft.
everybody
I
say
have
that?
I'm going deaf. Could you come up and use the
No,
mic?
to his point, right? Who are the users of that?
So Volta
Today?
so there's a guy from Volta Networks who's working on it, and he submitted a pull request a couple of days ago to start this ripping apart. I've actually started working on it myself, and over the last 6 months or so, I started that work. The synchronous to asynchronous, there's just a lot of work there.
So there's a Netlink backend which nobody uses today? Or?
It's there. I'm not aware of anyone using it. There's a lot of, it's with most things, there's a million little features that someone's thrown at
It's
it.
pretty old, is it? Somebody
Yeah,
else
it's probably been 2 years, 3 years since it was put in.
And the last question I had was, how many RFCs are there?
All of them. There's a lot. I mean, we have probably close to 30 feature requests that people have asked for. I basically tell people, sounds awesome. Bring me code. Yeah, you can't, right? So, and I work for Cumulus, and I do what is best for Cumulus. And someone with an RFC that matters for a non-data center usage, I'm not going to spend a whole lot of time on. Any other questions? All right, thank you.